started? Hello everyone, thanks for coming. It's my pleasure to introduce Mark. He's an assistant professor in Technion, and he's going to tell us about his work on general application offload to near network processors. Mark, off to you.
Hi, it's great to be here, and apparently the room was fully packed, so it's very nice. Right, so let me first of all tell you that it's a challenge to give this talk in front of the super technical, highly skilled audience, because usually I give this talk, in front of like students, and so I don't expect the level of understanding that I get here. So I will be very quick on some slides. Stop me or speed me up if I'm too slow. Right. So I want to start with motivation, and I shouldn't be spending too much time on this slide. CPUs are slow, networks are fast, you don't have time to process up to line speed, packets are small, usual stuff. You can do a fixed function offload. A fixed function offload is not really good because things are changing fast. And actually, I'm preaching to the choir here, in the company that deployed over 1 million of FPGAs around the data center. I shouldn't be telling this. So you're already convinced, and so surprise, surprise, there are things outside of the Microsoft Research and Catapult project that do very similar things. And this is in particular Mellanox FPGA-enabled NIC. So what you can see is there is a bump in the wire right on the wire between the NIC and the rest of the world, and actually NIC is sitting on the PCI bus, and it's a regular NIC. It's really important in particular for Mellanox and other vendors, not to change the silicon on the NIC itself, because this is very expensive. So they basically almost have no changes on the NIC in the silicon. It's just really a blip on the wire that everything goes through, and go and figure out how to use it. Right. So again, this is a very easy to sell slide here in this audience. The first bullet, go and ask questions about it, right? I don't expect this. But in the second bullet, it turns out that I think that it's pretty clear that the industry is either following Microsoft, or Microsoft is somewhat leading the industry. I don't know where chicken and egg. Clearly, the technology trend is toward adoption of this kind of architecture. And so the takeaway is this hardware is here. It's becoming popular, it's becoming widely available. What can we do with it? And what usually people do with it is pretty kind of infrastructural stuff. That's what really hurts in terms of performance. In data centers, you want to offload infrastructural stuff for virtual networking or encryption, compression, and etc. So this is our usual suspects. And I believe that Catapult is being actively used for this specifically. There is also another type of offload where you use this basically as an accelerator. So you have an FPGA accelerated applications. You just push them into FPGA. It happily sitting on the NIC, but it doesn't matter that it's on the NIC. You just don't use that. Or you can connect to this FPGA and just offload computes there. So things are pretty expected, and I think no surprises here. You probably know it even better than me. However, what we are trying to kind of think out loud here is whether it makes sense to really take IO-intensive applications and push some of them and basically accelerate them with the help of this interesting hardware that is available. And again, this is there's a subtle difference between what people have been doing with it before and what we are proposing here, because usually it was infrastructure, it was general, and I will actually highlight the main differences that stem from the fact that we are targeting general purpose applications here. So why moving some of the application logic on the NIC? Again, people have already shown that doing things in hardware is much faster than doing that in software, apparently. It reduces a lot of I/O bottlenecks on the host. How power efficiency, so all the goodies that FPGAs can do for you already, but now in a single package that it's really close to the NIC, and NIC is really close to the host, and it's also going to be available. So why don't we try using it? Right, so this talk is going to be, to start with, kind of high-level introduction or high-level overview of why we think, or what applications would be suitable for this kind of hardware. And then I will go and get a little bit more technical with the actual solution that we propose in order to support those applications. Design and implementation a little bit of evaluation, and then a bigger picture, which I believe is very important to keep in mind, because we're not dealing with just network cards in isolation. We really have to think in a broad perspective of what these future accelerated systems will look like and how this thing actually fits into this puzzle. I would also invite to ask questions on the way. It would make it much easier because my kind of stack is pretty shallow. So I will not remember what I told you before after the lecture. Okay, so let's start with a simple example. The example is really kind of engineered to show the benefits of network application offloading. And what I want to do here in this example is to explain why I believe that this particular type of architecture of bump in the wire NICs is the best one that suits the purpose of accelerating this type of workload. And then we'll see other applications and type of applications that would be suitable. So, okay, so you have the very simple anomaly detection service. This anomaly detection service does really simple thing. It receives some data. It checks the model whether the invokes the classifier, whether the sensor reading or some event is normal or abnormal, and in the case of normal event, it just drops or records some of the statistics, and if it's abnormal, then it alerts and probably updates the model as well. So this is a pretty common, I would say, anomaly detection service where the classifier can be of any complexity as you wish, from very simple, just averaging or thresholding, to a very complex of, doing some fancy classification like deep neural networks or whatnot. Right, so now we want to accelerate this, and the question is which architecture or system architecture would be the most suitable for acceleration of this kind of workloads. So let's start with a kind of normal, usual accelerators, GPUs or FPGAs that sit in PCI bus. Let's try that. So what we can use this for is to offload the compute part of this workload, of this application. And in order to do that, basically what you do is you put the classifier and probably the model update logic on the accelerator, but everything else is being handled on CPU. So the packets go through PCI bus to the CPU first, and then they get shuffled into the accelerator and then back. And so you can clearly see that there is a lot of stuff going on the bus that is totally redundant, in a sense that the packets get moved back and forth from CPU to the accelerator and back, and so it's a little bit of a mess. In terms of the efficiency, it's definitely not where we want to be, in particular if the classifier is pretty simple, right? So this would not be really good to push the classifier that is simple threshold into the accelerator in this case. Okay, so what are the other options? Another option is something that is commonly used or promoted in net FPGA community, I guess, where the accelerator is a standalone FPGA with a NIC, and you can just offload some stuff in there and use it as a separate machine, if you will, but just with FPGA. And so in this case, what you see is offloading everything, right? This is one model. And this is clearly very complex, because if you want really to push the whole application with 10 lines of code that you really want to accelerate and another million that you have to accelerate or have to put on this thing. So basically development is becoming a real pain, right? And you can clearly see things like Xeon Phi, where the claim for fame was that you just put the whole application on the accelerator and everything runs smoothly, but it runs smoothly but very slowly, and actually not so smoothly. So eventually, this model is really hard to work with from the development perspective. Right, so, and another case of standalone accelerator is basically, although it's standalone, you will still use the Ethernet, to connect to it and, push computations to it. It's very simple. It's very similar to the PCI kind of model, but it's just over the network. And so here you clearly see that there are problems again with the extra network bandwidth that gets consumed just without any reason. Right, and so here comes the savior, right? So here comes the bump in the wire design, where the nice thing about it is that the NIC is tightly coupled with the CPU, but it's also tightly coupled with the accelerator. So because of this, the cost of basically pushing data back and forth between the accelerator and the NIC is zero, because they're really close together, right? Now, what it really gives you is the ability to basically take the data on the flight and process it on the accelerator, and then maybe even drop some of it without pushing down to the host. So it's clear that you do some kind of filtering. It's very efficient because it basically piggybacks on network processing here, and that is the key to allow very lightweight type of offloads, right? Like even thresholding would really work well, because it's not that you would accelerate the threshold computation itself. You would accelerate everything that includes the network processing, plus you would piggyback on that for threshold computation, and then you would filter quite a lot of traffic, because again, we're assuming here that anomaly detection would usually encounter normal cases, normal events. What is really important, though, that most of the logic that you want to keep on CPU can, because again, it's very close to the NIC. So if you want to do some rare, something like model updates, you can do it even quite frequently, and CPU can trigger that without wasting cycles or without wasting too much time on communicating with this accelerator. Okay, so this is just a template for one type of workload that it seems to me would make sense in case of this converged architecture. Okay, now, the very very natural question to ask, is that it? Like, this is the only workload, so let's do and build infrastructure for a single workload? That does not sound too appealing. So let's go and try to do some analysis of what kind of workloads would really fit this architecture. So one thing that makes sense is filtering, right? And again, what we can do here is to basically transform the traffic coming in or going out in a way where you compress, or you drop a lot of the packets or a lot of the traffic that comes in, and you do the fast path processing on the NIC. But then you do the heavy weighting for the rare cases where you actually need some handling of this stuff on CPU. And you can think about data analytics workloads that just do some statistical analysis on the data. Some caching, for example, is a classical example for this kind of filtering, and we will show in the end of this talk. I will show how to build a little memcached cache that does exactly that. Another obvious example is data transformation. You want to do serialization, deserialization. You want to batch things together and give it out to the application already in a packed form. But it also can be used for optimized GPU and storage layout. So you can really go from the NIC directly to GPU and pack the data so that GPU would not need to parse it. You can think about all other different things like sampling that is really bad for all these regular type of accelerators like GPU that cannot really do sampling properly, because sampling involves very irregular memory access, so you kind of lose a lot of efficiency. If you can do that on this architecture and already prepare the data and give it to the GPU, suddenly GPU becomes more appealing for other for this type of workloads. Steering is another case where you don't want to rely on the infrastructural kind of steering like RSS, in order to be aware of the, let's say, load in different processors. So it's like a load balancer, if you think, for internal machine, but it's also application aware, so it can parse some of the data and figure out where to put the data in the machine, whether it's GPU, it can be another NIC, and can be whatever you want. Okay, so this is steering. And last but not least, generation. So you can think about different use cases where you would want to offload some basically packet generation or I would say network message generation cases. For example, in consensus, you would want to offload that. And actually, people did the standalone box for consensus acceleration. This might be a really nice case because most of the consensus actually would run close to either partially on CPU, so some weird cases would be handled by CPU, but the most common would be handled by the NIC. It could be also a MapReduce shuffle, for example, right? So if you think about it, if you're doing word count, all that you need is to get some data from storage and kind of push it up to the NIC where it would do the mapping, very easy streaming like mapping. And then according to the key, it would send it to the right reducer without involving CPU altogether. So again, what you see here is four types of, like, I'm not sure how completely orthogonal they are, but they definitely some overlap. So the classification is not super rigid. But I think that these four types of workloads already kind of make sense in terms of trying and pursuing the idea of making it all possible and not super hard to use this hardware for this type of workloads. Okay, so in hope that I have convinced you that it makes sense, now let me tell you why it is not that easy. Okay. So just a reminder, I'm sure you know that this is how a regular application looks like, right? So you have the NIC that is basically to a degree protected from the application by the network stack. An application never really goes all the way into the NIC. It just talks to the network stack, and network stack goes and controls the NIC. If you really want to do what we want to do with offloading some part of the application logic, you really need to basically push part of the application into the NIC, so that now the application actually combines two components here, one running in the NIC and another in CPU. And apparently data at the control are going very different paths, because now the control of the application should stretch all the way down to the part of the application running in the NIC. And the data may go also directly between the application and the NIC without passing through the network stack. So things definitely change here. So let's kind of go one by one and see what these changes imply in terms of the system infrastructure. Before I continue, so you would imagine that this FPGA comes with some nice framework to develop applications in it, right? Because vendors are probably very interested in this kind of applications. Well, surprise, surprise, they're not. They're not, because basically the killer app is infrastructure acceleration. So what they give there is very rudimentary set of tools or abstractions, if you can call this abstractions at all. These are things that you can use in order to implement infrastructure acceleration. So you can, there are low-level interfaces like ports, to other side of the network or the host. And there are a stream of bytes. You see raw bytes. This is not like packets or L3, L4 level messages. And you also get some buffer management. Very, very rudimentary at the level of like Ethernet tokens and stuff like that. So really, really low level stuff. I'm sure you don't want to deal with that. Okay.
Clarification. So often you also get cases in which the application talks directly to the FPGA over the PCI bus and do things like set memory and stuff. So how would that kind of change?
Right. So you're right. So in this particular scenario, I'm not saying that it's impossible. Okay, it is actually possible and doable what you're asking, right? If I understand the question correctly. So you're asking, what if the application wants to update memory directly over PCI bus? How does that come into this picture? Is that correct? Yeah. So when I'm looking at the control, I'm not exactly specifying how this control is being done. Does it go through the NIC specifically, which is the case for the architecture that we work with, or it goes through PCI? But it doesn't really matter for the purpose of the definition of interfaces. And I just want to know that there is a control, and it's not on the kind of data path, if you will. So I will talk a little bit about.
Even the data path can go straight from the application to the FPGA, right?
Yeah.
You can basically send data back and forth by just sharing memory.
Right.
To go through the network stack on the NIC.
That's correct, and this is what we are going to do as well, right? So the picture is kind of cutting through the network stack. It's not necessarily goes through the network stack.
Maybe just to clarify, can the FPGA in the architecture you're using access memory over the PCI or no?
Not yet. It will be in the second generation. Okay, but again, for the purpose of the discussion, what kind of things we want, I think that this is less of a issue. Okay, so let's start with the kind of going in detail over the challenges here, right? So first of all, we need to add some weight for the CPU application to interact with the offloaded part, right? So you have some state here, and this state definitely needs to be communicated or updated together between this part and that part. As I mentioned, there should be some network stack interaction because some data can pass through or go over it. So there is also some issue with the fact that the FPGA would want to send packets. So some of the tables, like neighbor table, is actually on the side of the network stack. So how do you make sure that this table makes all the way into the FPGA for this functionality to be available there? And there is application control. Apparently you want to start and stop and invoke the applications on this side, on the FPGA side, which is definitely something that is not available today. Okay, another interesting question is how do you program this thing, assuming that all the CPU side is being taken care of? What kind of interfaces you need inside the FPGA in order to support this kind of functionality? So today there is no way to expose state in a proper way. There are no interfaces for that. You see only raw packets, so some kind of parsing is necessary and support for high-level protocols. As I mentioned, there are only very rudimentary low-level protocols, low-level interfaces for sending and receiving data, which also definitely makes things really hard to operate. But here comes the really interesting part, right? And the really interesting part is that usually your machine is not a single application accelerator, right? Or a single application workload. You have a bunch of applications, you have a lot of processes, and suddenly when you want to allow general purpose acceleration and not infrastructure level acceleration, you really have to provide kind of, CPU-ish kind of protection and isolation, not only on the CPU side, which is done by the operating system, but also inside the FPGA. And this becomes already interesting because there are a lot of interesting issues that come up here where what does it mean really isolation and protection, and what does it mean for this kind of processing to be protected and against what? Okay, so let's start from very simple problem. The application on the white application on the right side can easily get access to state for the blue application on the left side. And this is not good. This shouldn't happen, right? And that's pretty clear. Another problem is that because the FPGA is completely ignorant to all the applications on the CPU end, it's not clear, or basically it's clear that all the application, all the offloaded parts will be able to see all the packets, which is absolutely unacceptable apparently, because that messes up the basic premises of like network abstraction on CPU. But another interesting problem here that the applications running on the NIC can actually monopolize it, right? Because there's no kind of rate limiting that is enforced. If you can see in this architecture, the NIC is kind of after the FPGA, right? So even the rate limiting that might be available in the NIC would not be actually applicable or would not work for this kind of architecture. But there are also other things, for example, spoofing, right? Think about it that now the FPGA may actually be able to inject packets belonging to, basically spoof packets to another application, effectively, breaking the basic semantics of this application as well. So you shouldn't receive packets that do not belong to you, right? So this is easily accessible. And last but not least, because this is a general purpose offload, so you really want other applications that do not use FPGA, and there are plenty of those, I believe, on those servers. You don't want them to be affected by something that is running on FPGA. So you really have to have this bypass over this whole FPGA logic, and you want to isolate that from the rest of the logic that is running there. So essentially, what you have here is a bunch of requirements that are derived from a sheer fact that all that you want to do is to accelerate not the infrastructure, but the application itself. And to handle that, we need to introduce several new abstractions and, I would say, another runtime environment that helps us achieve these goals and basically overcome those challenges, both on the CPU side and inside the NIC. Now, in the whole talk, I kind of mix and use the fact that it's FPGA on the NIC, but practically it can be any other architecture, because I don't think that whatever we are doing here is specialized for the FPGA. Whatever processor you would have on the NIC, you would still need to achieve or basically break those or overcome those challenges that I outlined earlier.
The programming model would be very different.
The programming model inside the NIC would be different, but the services that are expected on the NIC would be the same. Okay, so again, I'm not really saying that we are proposing a programming model for the NIC. This is kind of complementary. If you think about it, I have not said a word about how whether we program Vivado HLS, Verilog or OpenCL, I don't know, your favorite FPGA programming stuff. I mean, whatever I said here was just about the high-level interfaces that I would need, and how you provide them, that's your choice. So the key abstraction that we introduce here is that of what we call ikernel, right? So when we originally started thinking about it, our first idea was, okay, let's use something like GPU. You invoke, or any accelerator, you just invoke, and you tear it down whenever whenever you need to stop it. But it turns out that because this is tightly coupled with the networking kind of infrastructure, you really need to do something that is much more network specific in the spirit of network processing, if you will. So from that perspective, what we want to provide is we want to encapsulate the application code and state on the NIC through this abstraction ikernel, but what really makes it special is the way you use it. And the way you use it is that you take your open socket that already communicates with the rest of the system, and you attach this ikernel to this thing, okay? So this attachment process basically invokes the logic or reroutes everything that was supposed to arrive at the socket or to leave it, basically reroutes it through this ikernel, okay? Now, it is very similar to the concept of extended Berkeley packet filters to a degree. And actually there was a recent proposal to provide eBPF that actually attached to socket and not to at the infrastructural level. So I'm not claiming that this abstraction is super novel from the perspective of the network community, but definitely it is something that helps establish a much tighter link between acceleration of networking and accelerators in general. Yes?
Just a question. So does this mean that every application running on the iNIC must have a counterpart in the OS?
Precisely.
Okay,
Precisely.
so you cannot have a, so effectively means that you cannot completely bypass the CPU.
I cannot completely, no, okay. So
Because
completely bypass is an interesting question that I will also address in the end of this talk, right? Completely meaning you don't want the CPU even to initialize it. Yeah, I think we need to have some grounding on the CPU here in this abstraction. Data paths, that's a different story, right? All right, so let me give you kind of a glimpse into how it actually looks like. I will introduce the interfaces that we use by example. Okay, so the example is really simple. This is an anomaly detection service, really stupid one, right? Very, very simple. You have a have a bunch of thermal sensors that send their data. You want to know whether the temperature is rising somewhere beyond a certain threshold, above a certain threshold. And if it does, you want to fire some alarm or something. Okay, so very, very simple. And all the data that comes in, you want to update some kind of counter that gives you the average and the number of alerts and stuff like that. You want to accelerate it on this iNIC and with the use of ikernel. And the idea is basically that you really offload the threshold comparison to the iNIC. And all the alerts are going to be handled by the CPU. Makes sense, right? So what I really want to show to you is the code, right? So it is not the exact code that we have, right? But it's very close. So first of all, you create the ikernel, right? And this creation is a process that is kind of not defined in the specification, right? So it's do it how you wish. If it's FPGA, it will just link some kind of UID from there to here. But it will also initialize a whole bunch of other things. Then we have a set parameter that we want to initialize the state in the iNIC, in the ikernel. Then we just create the socket, regular stuff, nothing unusual. And then you attach. And so from the point you attach, this is where the traffic starts flowing. Okay, so you can ask all different questions like, how do you make sure that some of the packets are not already in the CPU? And there are all these kind of bootstrapping issues. Let's not talk about it for now. And then from that point on, what happens is that the host is going to issue just regular POSIX calls, nothing special. But with the catch that the only kind of packets or the only messages that it's going to receive are those that are passed by the ikernel, and many of others are going to be handled by the ikernel itself. And so therefore, what we know for sure that the message that is going to be arriving over here is the one that needs to trigger the alert, because all the normal messages are handled by the ikernel. So from that point on, after the alert is triggered, or even actually before that, you want to get the average temperature. That's where you retrieve some kind of state from the iNIC before you actually going and triggering the alert. And finally, you do detach and destroy, okay, after the application is done. So a couple of important things to understand about this model, right? First of all, it works dynamically, right? So you can attach or detach the ikernel whenever you want. Then you use just regular POSIX, right? It's not the only way to communicate. I will talk about data path later. But this is really the key kind of advantage of this architecture, because it's really backward compatible and it supports legacy as you wish. So if you just comment out all the IK prefixed calls, it will just work. There's nothing that requires special attention here. And another interesting part here is this IK command, which is basically an RPC call into the FPGA that allows you to both invoke some logic that would basically eventually provide or retrieve the state, or will do some computations, but it is not a shared memory kind of interface, right? And it's done deliberately because otherwise it's very hard to provide high performance from the ikernel itself, because it would have to go to the memory that is shared between the CPU and the iNIC, and that is a serious issue in terms of performance. This kind of memory is much slower. Yeah.
So where is the app itself, the terminal app?
Okay, just hold on, hold your breath. Yeah.
In this model, you always assume that all packets will always go to basically the CPU and the network stack.
No.
But how would you do with TCP state and stuff like that?
Right. So again, I expected this question to come earlier, but we are going to support only UDP. Okay, from this point. Okay, practicality of this approach is questionable. Okay, it's limited. It's not questionable. It's limited. But TCP is really hard to do. People have done TCP stack on FPGAs. We haven't gone to that point. And as far as I heard, Catapult also decided to kind of forego TCP and build something on top of UDP that is reliable and proprietary. So, the complexity of the thing is I probably deserves a couple of other talks. But you're right. For the type of protocols that we want to support, we definitely want to push all the protocol handling onto FPGA for now. We have some ideas how to combine this, but with CPU, but it's kind of very hazy so far.
Just to clarify, so you're not supporting any TCP
No,
application?
not yet. Okay. TCP is a kind of significant undertaking, I would say. Okay, so let's look at the other side of the divide, right? What happens on the iNIC? And what happens on the iNIC is like 3 types of interfaces. Some of them refer to the I/O channels, basically the way to communicate with the host and with the network. Another is data access and protocol processing, like passing the packets, decisions whether the packets are going to be or messages are going to be passed to the host or not. And finally, the ikernel control and state access, which is going to be implemented through RPC. And so let me show very quickly kind of a little bit more details on these interfaces. So the data input is coming from 2 virtual ports. And why are they virtual? Like host and network, right? 2 sides. But why are those virtual interfaces? Those are virtual because they're actually shared across all the ikernels as well as the bypass. And so it is the responsibility of GAON to multiplex those in a way that would prevent abuse of these interfaces or denial of service and stuff like that. So basically rate limiting and multiplexing, this is a shared resource that we need to handle. Another is that apparently the ikernel cannot observe the data that belongs to other processes. And so anything that is going to the socket and from, these are the only packets that the ikernel is going to observe. And now there is this control interface that allows us to draw packets, to create new packets, and to pass them to the other side effectively.
Quick question,
yeah.
Are you allowing modification of packets as well? Because you need that for things like compression.
Of course, yeah, sure. So that I'm going to be talking about that, next part, right? So basically, what I'm going to provide here is the interface that is at this point very FPGA specific, or I would say not FPGA specific. It's very specific to pipelined way of processing networking, because pipelining is the #1 concern. In order to sustain line rate, right? You cannot possibly do everything in a single cycle. So you really have to pipeline. And by breaking the data coming in into what actually some of your colleagues called fleet in Click and P paper. So the fleet is this piece of data that effectively matches the bus width, and it can be received all in one cycle. And so you can actually process it in as many cycles as you want in order to, if you can pipeline it, and then you would sustain the line rate. But this is something that basically is, in a way, dictated by the architecture. And so by breaking this, you can in parallel process, basically in pipelined way, different flits. This is the interface that we provide. The packets are parsed in metadata and data, so you can actually modify whatever you want in the way you want, and as well as drop, as is already clear from previous part. And so now in terms of the state, as I mentioned, there is this RPC interface that really helps to implement some of the functionality. And so let's go and show how it really works. Okay, so what kind of code you write. And so the code that I'm writing here is a very, very cleared up version of Vivado HLS implementation of this very simple kernel that I mentioned. It's not too far from reality, but it's not the reality, okay? So what here you can see is that it's event-driven model, right? On every event, the ikernel gets invoked. And so there is this call called on-flit, right? And so you get the flit itself. And then you figure out whether it's the first flit, so it's like the beginning of the packet. So basically it gives you kind of the location in a way. And so then you have to parse in a way that you want. You have to parse the packet. And we know that the first bytes of this packet are going to are going to contain the actual data. So this is going to be parsed here. Then there is this comparison, and then you decide whether you drop the packet or you pass it, right? Very simple. And in parallel also update the counters. So what you can see here is that it is very clear that you have to report to the interfaces that you're going to drop this packet. Or you can go and, or you can go and pass it. Okay, so if you pass it, it's a different control path. In the next iteration of this, you are going to be handling this part, which is basically writing flit to the host site. Okay, make sense? Okay. Now this is the interface that allows you to retrieve and update state, and this is a generic interface that is private to the ikernel, okay? And so you're going to be able to retrieve the state or even perform some computations of the critical path, right? So there will be logic that will be generated specifically for that, and this logic is going to be accessing some of the state that is shared by the main data path logic in the ikernel. But this is definitely not on the critical path. This is a slow path. Okay, so you're not expected to kind of stream data in and out by using this thing. In particular, for this simple example, right, in order to set threshold, you go and set it. So this is something that you can implement any way you want. All right, so the complete design looks like this. There is one side that is over here. It handles all the isolation protection, rate limiting anti-spoofing, and also implements all the interfaces that I just mentioned. And there is this whole thing that integrates with the network stack. And I will really briefly talk about the data path specifically because not only network stack, you don't need network stack in some cases. You can actually bypass it. Okay, so let's talk about data path. This is kind of the most interesting part, like getting a little bit more technical even further. So the first way to do data path, as I mentioned, is to support legacy through POSIX. That's easy. But there's another type of interface that we provide, which we call custom ring. Okay, so custom ring is something for advanced users. Okay, if so far it was really simple, now it's for advanced. So what you're going to do here is you're going to create a special abstraction that would be somehow implemented in the NIC that would allow you to access specific ring, both for TX and RX, inside the host. And that means that all the network stack is completely bypassed at this point. Okay, so the only thing that makes it very different from RDMA, for example, is the fact that it's not RDMA, because it's a ring, right? So there will be some kind of, there is some kind of actual network ring, but instead of network packets that need to be parsed by the stack, there will be actual application messages that will just be stuck up in this ring. Okay, and this is really convenient to basically offload a lot of the network processing off the critical path on the host, if it so happens that the host is also loaded with packets. But there are many uses for this. If you think about it, there are really plenty of uses, and therefore I'm really looking forward to this functionality to actually work. So far it's been pretty buggy. But once it's available, we can do a lot of things. We can do actual batching, because now application can get the real the messages in a batch form. We can do application level steering. Like everything that I said that I want to do, we will be able to do by sheer fact that we would have this custom ring abstraction. So another interesting fact here that is to a degree downside of this bump in the wire architecture is something that turned out to be an interesting twist in the fact in the story. So look at this. You have a FPGA. The actual structure of the NIC looks like this. There is a FPGA with two physical interfaces, that do the Ethernet and physical layer. And then there is a NIC, and then there is a CPU. And what happens here on the way is that from here to here, it's a basically lossy Ethernet, right? There's nothing special about this interface for the NetFPGA, for the iNIC kind of infrastructure, for the bump in the wire. And what it really means is that packets can be dropped. Now, it's totally legitimate to drop packets in regular Ethernet, right? As you can imagine. But the problem, yes, sorry?
I'm sorry for interrupting. So what is that link between the CPU and the NIC then? It's not the PCIe anymore?
Right, it is PCIe, but on the hardware level, you send packets very reliably. But it's not RDMA. So there is a protocol between the kind of high level of the stack, right? You have an Ethernet there.
But don't you have the credit-based scheme running on the PCIe that will do the control flow and ensure that the link is lossless? Right,
so PCI link is lossless. What is lossy is the fact that host may not be able to keep up with the processing the data coming from the NIC. Again, ignore this part. Ignore this thing. There's nothing. Okay, regular NIC. If you just send packets and the host cannot keep up, it will start dropping, right? But that's exactly what will going to happen.
The checksum can be wrong.
What?
The checksum you will check at the NIC maybe.
Checksum can be wrong is really rare occasion, but really what happens is that you are firing 40 gig at the host, it will not sustain. So the buffers will get overloaded, and story is over, right? It will start dropping. But here's the catch. The packets can be dropped, but suddenly this whole nice abstraction of extending application logic into the NIC suddenly breaks, right? Because suddenly there is, unreliable link between one function in the application and another function in the application. That really is not good, right? Okay, so when we figured that out, it was too late to fix it properly, okay? But it turns out that, if you think hard, what you can do is you still can work around it for most applications that we were interested in this at the first stage. But this is very clear that we need to implement the proper flow control between the iNIC itself and the side of the application, because otherwise some applications will just not work. So, for example, in the application where you have this, number of alerts, you count the number of alerts. If there are too many alerts and host starts dropping, this counter will be much higher than the actual number of alerts that the host will be able to handle. Okay? All right, so this is kind of a nitty-gritty detail. Yes?
So I'm interested, are you saying you believe that this is fundamentally the right way to construct this? Or are you saying this is essentially a bug in the fact that the FPGA is currently too far from the CPU, right? Because
that's a very good question.
Because there's two ways of addressing this. I mean, one is to say, the current thing about putting the FPGA essentially on the far side of the NIC is a temporary hack that we do right now, right? Where we basically have to re-digitize. We've got a fine link and then we lift the level again to do the processing on the FPGA, and then we lower it again to go out on the rail wire, right? And this is a kind of broken hack. Mm-hmm. And the right thing to do is to say, well, the NIC really ought to have, if you like, a coprocessor interface at the right point in the NIC, okay? And the FPGA should be plugged on that coprocessor interface, and then we don't have all this stupid, raising and relowering of the data as it goes through the abstraction, and therefore we wouldn't have this problem. Or maybe you were saying, yes, but the right point for that coprocessor interface in the NIC is actually still at the point in which you might have to deal with more cleverly with flow control between that processing unit and the CPU. So where are you on this space, right?
Okay, so it's a complicated question. Some of it I would be happy to take offline. We've been thinking about it a lot. Some of it is some answer is that the newer generations of the NICs and also Catapult 2, as a matter of fact, already allows direct link from the FPGA to the CPU through PCI. So effectively, you're not under the spell of network interface at all. So you can really have real flow control there. Is it a good idea for data path? I don't know. Quite frankly, so far we figured that the ability for the CPU to drop packets is actually essential to build applications with high performance. So if you would want to do this back pressure all the way down to the network, because some application gets stuck, it's not really clear that this is the best solution at the global kind of, at the grand scale of things.
Well, why isn't dropping packets the first thing you push to the FPGA?
Okay, that's a good point, because FPGA might not really know that it needs to drop packets because the host is already overloaded, right? So this is the matter of this is a subtle kind of question of flow control, how far it should go. Should it affect the FPGA as well, or should it affect only the fact when FPGA wants to talk to host? So and again, this is a really elaborate discussion that deserves probably a little bit longer than.
If you operate the link between the FPGA and the NIC at a tiny rate lower than the link between the NIC and the CPU, the FPGA will always know when to drop packets. As in, if you operate that at 39 gigs and the link from the NIC to the CPU is 40 gigs, the queuing will always happen at the FPGA, and it should be possible to always know when to drop.
I'm not saying that I cannot know when to drop. That's not the question. The question, I think, is whether I should be dropping before on FPGA, or I should be dropping on the host, or maybe the fact that FPGA would sit in the right place on the NIC would alleviate this problem. And the answer, and again, the answer is about lowering the stack, up and down. It's not clear that the solution of putting the FPGA after the NIC is going to alleviate this problem. For example, NIC does not support TCP mostly. Okay, so RDMA, maybe it's a different story. But again, there are a lot of things that could be done differently in a more efficient way if the FPGA would sit in the right point. But I'm not sure that this particular question would be addressed in this case. Okay, so again, let me rush through the kind of the evaluation part, because I think that what kind of maybe is a little bit of interest after all. So we implemented a bunch of applications. The first three are micro benchmarks, eco, traffic generator that just does kind of bursts of network sense. And then we have this look-through memcached and top-cake heavy hitters implemented on the NIC. And so I want to talk about memcached because this is the most elaborate, I think, example and the most interesting one. So I'll skip that and I'll get to memcached. So the memcached thing is actually a humongously large cache, as you can imagine, of 4K keys and values, each 10 bytes. So this is certainly a really, really prototypish thing just to understand how this thing can work eventually. We're not claiming that this is the real implementation. So the idea is that that this is a look-through cache. It's a very simple implementation, as I mentioned, really hash table basically. It's populated upon get, okay, and it's invalidated upon set. And what the reason for this is that if your set requests get dropped, then your cache in the NIC would be out of sync with those with the host. Okay, so therefore we definitely need to be very consistent with what host has in order to be able to, and because of this droppage, basically, this is the reason why it works this way. And so correctness is guaranteed in terms of the consistency of the cache with the host. Okay, so just one important point here to understand. The performance results that we got for 0% for 0 hit rate and 100% hit rate are remarkably, different, right? So the host is a really significant bottleneck here. So whatever host needs to handle it will be like 50 times slower than the NIC can do it right at basically line rate. And this is only 70% of line rate because there is some bug in the shell that does not allow us to generate packets quickly. But fundamentally, the throughput here is bounded by this formula, right? Which is with the CPU throughput. Because what happens when CPU becomes overloaded, it starts dropping, and at that point, there's no way. It doesn't matter whether the NIC is fast or not. The packets gets dropped, and so you actually have to back pressure at the application level. And so this is the theoretical kind of curve here that says this is how this should look like. But the measured is apparently very similar because that's how we regulate the load generator. Okay, so it should not come as a surprise. And then the question becomes, okay, you have very fast cache, but it's pretty tiny, and what can you possibly do? And so here, apparently, first of all, there are FPGAs and NICs with large memory, even large fast memory. But also the zip is really nice thing, right? The skewed distribution of accesses is going to allow us to handle with really small cache. We would be with a cache of size 1%, we would be able to handle 50% or 60% hit rate, which is nice, and it still gives us reasonable speed up here. Okay, so I'm going to skip to the lesson learned and really 3 slides maybe for the bigger picture. Sorry for taking 2 minutes more. I'm sorry about that. So what are the lessons learned? So kind of expected lessons for software people doing some hardware stuff, right? Hardware development sucks to the degree that it's just insane, and it burns out students, professors, and it's really not convenient. And I think it's an opportunity for those of us who actually got into this to introduce something new and useful. And that's what we've done with our debug interface. I didn't have time to talk about it. But the bigger picture is that the world is changing, and there will be a lot of programmable stuff lying around in your machine. And the programmable NICs are just one of those, but there are also GPUs and a bunch of others. And and although they're all nice and programmable, eventually you are faced with a really tough challenge, which is the programmability wall, right? Go and program the system with a bunch of accelerators, each one having some other constraints and low-level programming frameworks and whatnot, without any abstraction. So doing this is really tough. And so the goal that we kind of set out to achieve several years ago was to break this wall. Okay, and the way we are going to break this wall, we are going to break out the CPU-centric operating system architecture in the way that would allow us to get rid of the control and get rid of the CPU kind of being the only and single point of contact in order to do kind of operating system stuff and I/O and get operating system services. With the idea of building a accelerator-centric operating system with the operating system services actually spread out over all these programmable devices. And we have done a little bit of work on that for GPUs with the file system and networking and RDMA support from GPUs. We are now doing that with NICs, and the next frontier is storage. And then basically the idea is to kind of build a coherent architecture that would allow something like unikernel that would have different library OSs running on each one of those and providing a coherent view of the state of the system without necessarily having the CPU involved in all that. So this is the bigger picture. This is where we're heading to. And with that, you can easily derive the future work that we have. Apparently, some of it is to improve whatever we already have. But there are also other things that, in particular, the last bullet is something that is of particular interest here. is the use of NIC to communicate and to invoke tasks on other devices and vice versa. So with that, I would like to thank you.
We don't really have time for questions, but Mark will be here in the afternoon, so we'll have the opportunity to talk with him. Thank you.
Excellent.